Hello and welcome to this presentation related to applying energy methods to angular motion. This is the introduction to the topic. This presentation essentially relates to applying the principle of conservation of energy to angular motion problems. In other words, we'll be applying the equation we used in a previous presentation related to linear motion, where we consider the initial energy of the system and any work put into the system, and we equate that to the final energy of the system and any work out of the system. Here's a brief overview of the presentation related to angular motion and the application of energy methods. Notice in the square brackets below are approximate timings when each of the sections in the presentation commence. The underpinning knowledge required to understand the methods and techniques used in this presentation commences 3 minutes in. The theory behind the angular kinetic energy commences 5 minutes in, and the principle of conservation of energy, something we reviewed in a previous presentation, is reviewed in an angular motion context starting 8 minutes into the presentation. Example 1 shows illustration of the above techniques by considering a shaft initially brought to rest and then accelerated back to its original speed. Example 1 commences 13 minutes into the presentation and is in two parts. Part A, we have to calculate the braking torque required to bring the shaft to rest, and Part B, we calculate the number of revolutions turned through to regain full speed. Then there are a series of exercises. Exercise 1, here a shaft is accelerated from rest against a friction couple, starts 22 minutes into the presentation, and here we calculate the accelerating torque T. Exercise 2, here a shaft is initially rotating with an angular velocity and we're increasing the speed of the shaft again against the friction couple. That starts 27 minutes into the presentation. Again we calculate the accelerating torque T. And exercise 3, here a shaft is brought to rest by friction effects including a friction brake, and exercise 3 starts 31 minutes into the presentation. In exercise 3, we'll refer to a friction model that we outlined in a previous presentation as we calculate the normal force applied to the brake block, symbol N. And finally, the presentation concludes with questions for you to attempt at your own pace, although full solutions are included. The questions commence 39 minutes into the presentation. As I said, these are approximate timings, but hopefully help you find particular sections within the presentation as required. This presentation does assume some underpinning knowledge. Firstly, that we're familiar with the linear energy equations. From our previous presentation, work done, W was equal force multiplied by distance, and kinetic energy was equal to the mass of the object multiplied by the velocity squared divided by 2, or half mv squared. We did also consider potential energy, but that's not something we'll consider in this particular presentation. Also be aware of velocity time diagrams, particularly angular velocity time diagrams, where we plot the angular velocity omega in radians per second, shown here on the diagram, against time t on the horizontal axis in seconds. And of course there's an array of equations related to angular motion that we derive from the diagram, and again we'll be referring to some of these within this presentation. As already mentioned, we need to be aware of the principle of conservation of energy. Again, we used that in a previous presentation. And also Newton's second law applied to angular motion, the T is equal to I alpha equation, and again there's a separate presentation related to that derivation and application. So that's underpinning knowledge that's very useful for you to be aware of before progressing with this presentation. We'll refer to some of these quantities and some of these equations in the work we're going to review. So let's consider angular kinetic energy. If we consider the work done in accelerating a shaft, having a moment of inertia, symbol I, from an initial speed, omega I, to a final speed, omega f, whilst turning through an angle theta measured in radians. So here's our shaft rotating, motion shown here with the angular velocity omega. There's a torque applied to the shaft, and that induces an angular acceleration. Here's Newton's second law applied to the angular motion. The torque is equal to the moment of inertia multiplied by the angular acceleration, usually shown as alpha. So that's our rotating shaft or rotating disc that's subject to an acceleration. So from Newton's equation of motion as applied to angular motion, we previously derived this equation of omega f squared is equal to omega I squared plus 2 alpha theta. If we rearrange to find what's termed the average angular acceleration, alpha, that now equals to the omega f minus omega I squared, or divided by 2 multiplied by theta. Now we know from Newton's second law, as applied to angular motion, that t is equal to I alpha. And if we now substitute this expression for alpha into Newton's second law, we end up with this equation for t. Here's the substitution. Now recalling from our linear motion presentation, work done in a linear sense is force multiplied by distance travelled. Work done by the rotating shaft in an angular sense, where the displacement is theta in radians, is written as t theta. So t multiplied by theta in the angular sense is equivalent to force multiplied by distance in the linear sense. So remember, work done in the linear sense is equal to force multiplied by distance, or sometimes termed displacement. So finally, expanding the brackets, work done in the angular sense, t theta, is a half I omega f squared minus the half I omega I squared. And of course, work done is energy, and the unit of energy is the Newton meter or the joule. So note that the half I omega squared term is known as the kinetic energy of rotation. And note the analogy between the kinetic energy of linear motion, that's a half mv squared. Let's consider now the principle of conservation of energy. So to solve the following problems, we're going to use the conservation of energy equation, and as used previously, we will be applying this equation to the before and after considerations of the problem. So the way we apply the principle of the conservation of energy, on the left-hand side of our balance, which is essentially an energy balance, we have the initial energy of the system added to any work into the system, and on the right-hand side we have the final energy in the system and any work out of the system. So if we consider two different scenarios here, let's consider the energy equation for an accelerated shaft with friction considered here. We're assuming here that the shaft is already rotating with some initial angular velocity, omega I, and it will be increasing its speed and so have a final angular velocity, omega f. So we need to think of the initial energy. If the shaft or the disc is rotating, it will have kinetic energy of rotation, so that's the half I omega I squared. If the shaft is being accelerated, then it must mean there's some work into the system. So on the left-hand side, we'll add the t theta for the work into the system. After the work has been entered into the system, on the right-hand side of the equation, we will still have kinetic energy because we're assuming the shaft has been accelerated here. So I'll have the half I omega f squared term. And because friction is considered, we'll also have work out of the system. So I'll add my TF theta, TF standing for a frictional couple or frictional torque. So the TF theta term is the work done by friction. That comes out of the system. That will exhibit itself through heating of the shafts, heating of the environment, and so on. So in this case, we have 4 terms in this particular balance. And we can play tunes on this. If, for example, the shaft was not rotating to begin with, it was starting from rest, then we just simply would ignore this term. And we'll just have our work into the system to accelerate the shaft, and that goes into kinetic energy and, in this case, friction effects. If the shaft was starting from rest and had no friction considerations, then on the right hand side the TF theta term would disappear. In this case, all of the inputted work done would transfer directly into kinetic energy of the rotating shaft. So the same principle of conservation of energy is applied here, but we're playing tunes on the types of energy that are present initially and finally in the system. If we now consider an example of an energy equation for the shaft subject to braking with friction effects, by default the initial energy would purely be rotational energy, the half I omega I squared. So that's all we've got for the initial energy on the left hand side of the equation. There's no work into the system in this case. But on the right hand side, because we're applying brakes, we would assume that the speed is reducing, but we will still have a kinetic energy of rotation. So we still have half I omega F squared on the right hand side. But work will be done in 2 senses now. We have work done against the braking, so I've called that TB theta. That's work done by the brakes. And we would also have work done against friction, the TF theta, because we're considering friction effects still. So in this case, we have on the left hand side 1 energy term, but on the right hand side 3 energy terms for the problem as outlined. And again, we can play tunes on this equation. If friction effects from bearings, etc., was not to be considered in the problem, then we would ignore this term and just have the work out the system due to the braking effects here. And of course, if the shaft was actually brought to rest by the braking torque, then we would have no kinetic energy on the right hand side of the equation because the shaft is now motionless. So in this latter case, all the initial kinetic energy of rotation is purely transferred in the energy out the system due to the braking effect. So I hope that's provided a little overview of how we're going to apply our conservation of energy principle here. And it's a very similar approach to that we used in the previous presentation related to linear motion. I'm going to now take you through example 1 from our notes. We're going to solve this problem using the energy concept outlined previously. So again, we have a shaft having a moment of inertia of 32 kilogram meters squared. It's initially running at a speed of 10 revolutions per second. The shaft is brought to rest in 18 complete revolutions by a braking torque. It's then reversed and accelerated in the opposing direction back to 10 revs per second. The driving torque applied is 0.68 kilonewton meters. We're informed that there's a friction couple that can be considered to be constant throughout the operation of 170 newton meters. So for the first part of the question, we have to calculate the braking torque required to bring the shaft to rest, and then calculate the number of revolutions turned through in again attaining the full speed of 10 revs per second. So there's our question outlined. So let's first of all extract the information from the question, make sure we have the appropriate units, etc. The shaft moment of inertia, I, is 32 kilogram meters squared. Initial angular velocity, omega, is 10 revs per second. Number of revolutions to bring the shaft to rest, and the accelerating torque in the first part of the question, T, is 0.68 kilonewton meters in the question, so that's 680 newton meters. The constant frictional torque, TF, stated as 170 newton meters. So the first thing I would do is calculate the angular velocity, omega, in terms of radians per second. So in the question, the Angular velocity is 10 revolutions per second. Remember that in one revolution there are 2 pi radians, so multiply that by 2 pi. So 20 pi radians per second is the angular velocity that we initially have. So on the left hand side I've got my velocity time diagram. On the vertical axis I have my angular velocity, so there's the 20 pi. That's the initial angular velocity. So that's omega I. We know the final angular velocity for the first part of the question will be 0 because the shaft is being brought to rest before being accelerated in the opposite direction. The angle turn through before the shaft is brought to rest, I call that θ1 here. That's the 18 revolutions multiplied by 2 pi, so 36 pi radians. And that's effectively the area under the graph here, 36 pi radians. So that's the information extracted from the question. Example 1 continued. This is part A. We're calculating the braking torque required TB. So let's apply the principle of conservation of energy. Let's consider our initial energy and our work in equated to the final energy and any work out of the system. So from a velocity time diagram, the initial energy relates to the shaft's rotary motion. We know it has an angular velocity omega of 20 pi radians per second. So therefore it will have kinetic energy of rotation. There's no work into the system here because the shaft is not being accelerated. So it's just the one energy term on the left hand side of the equation. Considering the final energy, well, we know the shaft is brought to rest because we're told it reverses its direction and then increases its speed again, so it must come to a stop before it reverses its direction. So we know that the braking torque required brings the shaft to rest. So we'll definitely have the work done by the brakes in this case, so TB θ1. And we're also told in the question there's a constant frictional couple applied throughout, so there'll be work done against the friction, that's friction in the bearings, etc. So that's add TF θ1. So that's the right hand side of our equation, all related to work out of the system. Work done from the brakes used to bring the shaft to rest over the 18 revolutions, and also work done against the bearing friction, etc. Because the question wants us to find the braking torque, all we do now is simply rearrange the equation to find the braking torque. So on the next line I've simply subtracted the work done against the constant friction couple from both sides of the equation. And on the next line I've simply inserted the numerical values. So θ1 we know is 36 pi radians from the previous slide, so inserting θ1 into the equation. We know the moment of inertia, it's 32 kilogram meters squared, so inserting the I into the equation here. And the initial angular velocity was 20 pi radians per second. That's denoted as omega 1 here, so there's my 20 pi, and of course it's squared in the equation. And then simply evaluating the right hand side of the equation and dividing by 36 pi, we find that the braking torque required to bring the shaft to rest is 388.5 newton meters, or approximately 389 newton meters. So that's the first part of the example solved. Example 1, this is part B. In this case we have to calculate the number of revolutions, I've termed that as N2 here, turn through in achieving full speed again, and full speed of course will be back to the omega of 20 pi radians per second. In notation below, θ2 relates to the number of radians turned through in the shaft obtaining the full speed again. So the final answers must be given in revs, but don't forget in our calculations we have to use radians. So again, applying the principle of conservation of energy, here's our initial energy and our work into the system on the left hand side of the equation, and our final energy and the work out of the system on the right hand side. So considering our velocity time diagram for the second part of the question, now the shaft is commencing from rest, it's stationary as it changed its direction, and it's increasing its speed back up to the original speed of 20 pi radians per second, shown here. So if we consider the energy we have initially, we have no kinetic energy because the shaft is stationary, but we know that the shaft is being accelerated, so there must be work into the system. And I've denoted that as T theta 2. Now we have gained full speed, so by definition we must have kinetic energy of rotation. And of course we've got the constant frictional torque to overcome that takes work out of the system. We're trying to calculate theta 2 from this equation. So the first thing I'm going to do is rearrange the equation to get all the theta 2's on one side. So I'm going to subtract TF theta 2 from both sides of the equation on the next line. On the next line I'm factorising on theta 2 because it's common to both of the terms on the left hand side. And then finally I divide throughout by the bracket T minus TF to form an equation in terms of theta 2. Certain our values from the previous slide, we know what I is. So we can insert the I into the equation. We know the final angular velocity is 20 pi radians per second again, denoted that as omega f here. So omega f is 20 pi, and again it's squared. The applied torque required for acceleration is given in the question. That was 680 newton meters. And our friction torque is again constant of 170 newton meters. Evaluating the angular displacement, theta 2 is 123.9 radians, but we've got to state the final answer in terms of revolutions. So again, remembering that there are 2 pi radians in one revolution, we divide 123.9 by 2 pi. So the final answer is 19.7 revolutions to attain full speed. So example 1 has given us an insight into how we apply the principle of conservation of energy to angular motion problems. Let's consider some exercises. Exercise 1. A rotating shaft carries a load having a moment of inertia about the shaft axis of 48 kilograms meter squared. We're asked to calculate using an energy method torque required to accelerate the shaft from rest to a speed of 900 revs per minute in 12 revolutions. There's a constant bearing friction that's equivalent to a couple of 300 Newton meters. Answer stated in the bracket here. Again, extract the information from the question, make sure the units are converted where appropriate. I would suggest draw a velocity time diagram and then apply the energy balance considering the initial energy and any work into the system and then the final energy and any work out of the system. But I will show the full solution on the following slide. So exercise 1, solution. Extracting the information from the question, we know that the shaft moment of inertia I is 48 kilogram meter squared. The angular displacement, capital N here, in accelerating the shaft is 12 revolutions. I converted the N revs into theta radians here, so 12 revs multiplied by 2 pi, that's 24 pi radians, or 75.4 radians in decimal. Note that the 24 pi radians is the exact figure to use. And the angular velocity omega, given in the question, is 900 revs per minute. I converted that into an angular velocity, lowercase omega here, of radians per second. So 900 multiplied by 2 pi upon 60. That's 30 pi radians per second, or in decimal, 94.25 radians per second. So that's the maximum angular velocity of the shaft. And just note for reference, in this case, omega I would be the initial angular velocity, which is 0. Omega f would be the final angular velocity, which is the maximum angular velocity for this scenario. And the friction torque or friction couple stated in the question is 300 Newton meters. On the right hand side I've sketched the velocity time diagram. That's omega against t, omega in radians per second, t in seconds. We're informed in the question that the shaft accelerates from rest, so stationary initially, with a torque applied. That's assumed a constant torque applied, and thus produces a constant acceleration, so a linear line on the velocity time diagram, up to the maximum angular velocity, which is the 30 pi radians per second. Remember, the slope of the line is the angular acceleration symbol alpha. And of course the area under the line relates to angular displacement theta in radians. So exercise 1, solution continued here. Let's apply the principle of conservation of energy. Initial energy plus work in is equal to the final energy plus work out. So as the shaft starts from rest, there will be no initial kinetic energy on the left hand side, but there will be work into the system because we're accelerating the shaft. So I've called that TA is theta in this case. TA is my accelerating torque. And for our final scenario, when we're at maximum speed, we will now have the kinetic energy of rotation, the half I omega squared. And of course we'll have work out of the system, denoted as TF multiplied by theta, due to the constantly applied friction torque opposing the change in motion. We're asked to find in the question the accelerating torque, so just got to rearrange the equation for t. So I simply divide throughout by theta to produce this equation. Notice the first term is divided by theta, but in the second term these thetas have cancelled, so it's just the frictional torque here. Inserting the values for the I, moment of inertia, final angular velocity omega, angle turns are in pi radians, and of course the frictional couple. Evaluating, we find that the accelerating torque required is 3,127 Newton meters. I've just written it in terms of kilonewton meters here for reference. Exercise 2. Again, the shaft has a moment of inertia, 16 kilogram meters squared. It's accelerated from a speed of 1440 revs per minute to a maximum speed of 1500 revs per minute, and that's during 2 revolutions of the shaft. We're given a friction couple of 80 Newton meters constantly applied. We've got to calculate the average torque required to accelerate the shaft. The torque is given in the bracket here. Again, I would encourage you to stop the presentation and try and attempt this question, but I'll show you the full work solution on the following slide. Here's exercise 2, solution. Extract the information from the question. We know the moment of inertia, given in the question, 16 kilogram meter squared, 1400 revs per minute to 1500 revs per minute. So I've converted here my initial angular velocity from RPM into radians per second. So omega I is 48 pi radians per second. Also shown in a decimal here, if you prefer decimal values. And my final angular velocity is 1500 revs per minute, again converted into radians per second. We're told this happens during 2 revolutions. So again, converting my angular displacement from revs to radians, that's 4 pi radians. Friction couple, constantly applied here, would assume is 80 Newton meters. As always, I will sketch a velocity time diagram. On the vertical axis now I have my initial angular velocity, and that's 48 pi radians per second. And the final angular velocity, that's 50 pi radians per second. Exercise 2 solution continued here. We're calculating the accelerating torque T as required to increase the speed of the shaft. So again, applying our principle of conservation of energy, the initial energy plus any work into the system is equal to the final energy plus any work out of the system. From our velocity time diagram, we have initial kinetic energy because the shaft is rotating. So half I omega I squared on the left hand side. And we know that the speed of the shaft is increasing, so there must be some work into the system. So it would increase its kinetic energy, so we have a half I omega F squared on the right hand side. And we're told that there's a constant frictional couple, so we have work out the system done against done by the frictional couple. We're trying to find T in this case, so rearranging the equation, first of all I subtracted the half I omega I squared from both sides of the equation, and again divided throughout by theta to produce the equation for the torque. The next line I simply insert the values for I, moment of inertia, for the final angular velocity, for the initial angular velocity, for theta, and of course the friction couple. Evaluating the torque required to increase the speed is approximately 1312 Newton meters. Exercise 3, slightly more complicated problem here. We have a shaft rotating at 720 revs per minute. It has a moment of inertia of 34 kilogram meter squared. It's brought to rest by a brake block that acts on the rim of the 1 meter diameter drum. We've got to calculate the normal force on the brake block that contacts with the drum to bring the shaft to rest in 15 revolutions. We're given the coefficient of friction between the block and the drum is 0.45. There's also a few hints in the question. The torque applied by the braking system would be the frictional force multiplied by the radius of the drum, and we're also told that frictional force, Ff, is equal to mu times n. This is essentially referring back to our frictional model we reviewed in a previous presentation. The normal force required is stated in the bracket. Exercise 3. Here's a brief overview to the solution required. Our scenario here is a rotating shaft and drum. Initially has some angular velocity omega, and using a brake block on the outside surface of the drum, we're going to apply a normal force, shown here, labeled capital N, that will generate the frictional torque required to bring the shaft and drum to rest. So the first thing we need to do is to calculate the braking torque, which we can find if we apply the principle of conservation of energy as we have in previous exercises. Once we've applied the energy balance, we will be able to find TB, and knowing the radius of the drum stated in the question, R, we'll be able to find the frictional force required. Friction force Ff shown here. From a previous presentation, we considered a very simple frictional model that allows us to calculate the frictional force Ff. So now, having calculated the frictional force from our torque equation here, knowing the coefficient of friction stated in the question, we can finally determine the normal force N applied to our brake block. I would now encourage you to stop the presentation and attempt this question, but the full work solution will be shown on the following slides. Here's exercise 3, solution. Extracting the information from the question, we know the shaft is rotating at 720 RPM, so capital omega 720 RPM. Converted that into radians per second, so lowercase omega 24 pi radians per second. Moment of inertia of the shaft, I, 34 kilogram meter squared. And the drum has a 1 meter diameter, so capital D here is 1 meter. So the radius of the drum, we'll need to know that information later on, will be 0.5 meters. The number of revolutions in bringing the shaft to rest is stated as 15. So N is equal to 15 revs, and of course converted that into angular displacement in radians. That evaluates to 30 pi radians. The coefficient of friction given in the question between the block and the drum is 0.45. So symbol mu, 0.45. Sketching a velocity time diagram. The initial angular velocity is 24 pi radians per second. So that's it here. And the shaft is ultimately brought to rest. So the final angular velocity will be 0 in this case. Exercise 3, solution continued. I just repeated the angular velocity time diagram here and some information from the previous slide here for our convenience. Let's now apply the principle of conservation of energy. So initial energy plus any work into the system is equal to the final energy plus any work out of the system. So we know the shaft and the drum have an initial angular velocity of 24 pi radians per second. On the left hand side we'll have initial kinetic energy, but that's the only term on the left hand side. There's no work into the system here. And we know finally the shaft is brought to rest by the braking torque, so there's no angular kinetic energy term on the right hand side of the equation, but we do have work done by the braking torque, so TB theta on the right hand side. In this case we need to find the braking torque TB, so simply dividing both sides by theta we form an equation for the braking torque. So inserting the values into the equation, we know that the moment of inertia I is 34 kilogram meters squared. The initial angular velocity omega is 24 pi radians per second, so inserting that into the equation. And the angle turned through theta is 30 pi radians, so 30 pi into the equation. Evaluating, we find the braking torque required is 1025.4 Newton meters. Now we also know that the braking torque would be the frictional force multiplied by the radius of the drum. So now knowing the braking torque from above, knowing the radius from the question, we'll be able to determine the frictional force that's required to bring the drum to rest. And just for background information, let's consider our simple frictional model we reviewed in a previous presentation. Here we show an applied force P to a body that's resting on a surface. Frictional force opposes the direction of the relative motion, so that's opposite to the applied force P. And the model also shows the reaction force from the surface on the body, called a normal force N here. In most questions reviewed in the previous presentation on friction, the normal force tended to be equal to the weight force, but it does not have to be. So that's an empirical model from which we derive a very simple formula for friction. Frictional force is equal to the coefficient of friction, symbol mu, multiplied by the normal force N, and that will be newtons. That's essentially the model we're using for the brake block contacting the rim of the drum. Exercise 3 solution continued here. On the left hand side I've just repeated a frictional model for reference, and on the right hand side I've shown a depiction of the brake block contacting the rim of the drum, shown here. So we calculate our braking torque previously, the 1025.4 Newton meters. We know that braking torque is equal to the frictional force multiplied by the radius. We've got the radius from the question, it's 0.5 meters. So we can rearrange the equation to find the frictional force. It's simply the braking torque divided by the radius. Inserting the values, we find that the friction force required, shown here, is 2051 newtons. But we know that the frictional force is equal to the coefficient of friction multiplied by the normal force. So rearranging for the normal force N, it's the friction force divided by mu. Inserting the frictional force from above, the coefficient of friction was given in the question as 0.45. We can determine the normal force required to cause the braking effect is 4.56 kilonewtons. So that's this value here, forcing the brake pad onto the rim of the drum. I will leave you with some tutorial questions. I will show you the solutions to these questions, but I will let you review them at your own pace. So here are the first 3 questions, question 1, 2 and 3. Answers to each question are shown in the brackets here, but I'll very briefly outline the full solutions on the following slides. Here's question 1 solution. I'll let you review it at your own pace. Here's question 2 solution. I'll let you review this at your own pace. Question 3 solution, Extracting the information from the question here. Question 3 solution continued. Here's the energy balance to find the braking torque. Question 3 solution continued. We're using the equation of motion here to find the angular acceleration alpha. Notice it's negative because this is a retardation. It's an alternative way of calculating the angular retardation for reference. Using Newton's second law. Produces the same value of acceleration, of course. And here's one further tutorial question, question 4. Again, I would encourage you to start the presentation and attempt this question. There are 3 parts to the question and the answers are shown in the bracket here. The full work solution is shown on the following slide. Question 4, here's the solution. Firstly, extract the information from the question. Just note in this question we need to calculate the moment of inertia I. It's been given in the other questions. But we have the mass in the question and we can calculate the radius of gyration squared, the k squared value, because we know from a previous presentation for a solid circular disc the k squared value is d squared upon 8. So in this case we've calculated k squared. Diameter is given as 1600 millimeters, converted to meters here. Question 4, solution continued. This is part 1, calculating the work done during braking. I'll let you review this at your own pace. Answer stated here with the appropriate energy unit. Could also state that in kilojoules, of course. Question 4, solution continued. Part 2, calculating the braking torque, TB, shown here. And part 3, calculating the friction force on the rim, friction force shown here. Here's the bibliography used to help generate this presentation, and I hope it's been of interest to you, and thank you for viewing.